For unverified reasons, tennis balls have been accumulating in the Hardy lab. This accumulation presents a safety hazard which needs to be addressed. Collecting the tennis balls and throwing them into the bin by hand could have potential risks for repetitive strain injuries, shoulder dislocations, or other musculoskeletal injuries. So a mechanical solution for throwing the tennis balls with minimal strain was required. To arrive at the solution, other devices currently on the market were observed, as well as research reports on aerodynamic and ballistic characteristics of a tennis ball discussed. All other devices on the market fell short in at least one of the client's requirements. They relied on electrical power, they did not have the range required, were not accurate enough, or required too much force to fire. Based on the academic research we had consulted on tennis ball aerodynamics, it was determined that our requirements did not necessitate measures to counteract the knuckleball trajectory, and so we would not require any spin or any other such preventative measures applied to the tennis ball. For the ideation process, we discussed the requirements of the project and determined a set of objectives. Any solution must be accurate, quick to reload, have a large range of usable distances, be cost-effective, and durable. In considering these objectives, we considered devices based on medieval catapults, ballistas, a railgun, and a gravitational potential energy system, or giant swinging hammer. Because of the ease of construction, simplicity, and likelihood of successfully completing the objectives, as well as based on a pairwise comparison chart and weighted decision matrix, the ballista design was selected. Ballistas traditionally use an elastically deformed member that flexes, producing an energy potential. This device was adapted to make use of a spring with a linear spring constant to make calculations simpler and success more likely. Based on the mass of the tennis ball and carrier, the required exit velocity was determined, which allowed us to select an appropriate spring using conservation of energy. The trigger system had to be activated with only a 3 Newton force, so we chose to extend the spring displacement, allowing a lower spring constant and a lower ultimate force on the trigger mechanism, and, as such, a trigger mechanism with fewer moving parts and a higher degree of reliability. In order to reduce the materials required, a collar piece was designed to allow the unstretched spring to extend past the end of the barrel, allowing for adjustability of the spring position. This adjustability alone would not have been sufficient, so further adjustment was made available through a stand that would allow a variable firing angle. During initial testing, it was discovered that the carrier would develop a suction on the tennis ball, preventing its release after full extension. In order to prevent this, holes were drilled into the base of the holder. With this issue remedied, we arrived at our final design, nearly everything we hoped for. Using a lower spring constant gave us a long barrel, but left us with a small force on the trigger. Pulling the carrier back with ease, springs connected to the trigger locked the ball in place. The trigger is then pressed, launching the ball to the intended target. We were able to test the tennis ball launcher to the full range of its abilities with great success. Our solution was able to easily meet all the objectives and constraints we had set for it.